Angello is our next speaker. Your ball from the next paper, right? Great, okay.
Our work is focused on the safety of ML-based cyber-physical systems, such as autonomous vehicles that use vision-based perception. In these systems, ML modules enable perception tasks to estimate ground truth real values of the environment. For example, how far is the pedestrian away? We're interested in showing safety of such systems. An example of a safety property is for the car should not leave the current lane. So we pose a fundamental question here is, what exactly is a contract for ML vision components, and how can such contracts help us reason about system safety? Contracts for ML component, much like those in traditional software, consist of pre and post conditions. For example, the specification for robustness says for some input x and all inputs x prime within a ball of radius centered at x, for some radius centered at x, the output label of the original input x and the label of x prime should agree, right? That says something about the input and says something about the output. However, these kind of contracts cannot capture relevant objects for perception on images. This is a problem when we're trying to assure the safety of these systems. As you can see, the particular example is how would we be able to express from images that if the pedestrian is 5 meters away. So to address this, we propose perception contracts. But before I formally define it, I sort of want to discuss the insights that we make for the formal definition. So perception contracts are not usual module contracts. They do not relate inputs and outputs of an ML perception module. Rather, they relate the implicit ground truths associated with the image to the output ground truth estimates given by the perception module. As you can see in the top left corner, we have two kinds of perceptions. One that deals with a real environment interacting with the perception module via images, and another one where there's a model of the environment. There's a model of the environment that takes in feedback from the controller system, and gives you the ground truth values for a perception object. So as you can see here in the third diagram at the bottom, a perception contract, what it's really doing is relating this perception indicated in the blue line that deals with a real environment and ML-based perception, and this other sort of perception that involves working with a model of the environment. And in fact, if you notice, given that it is not clear how to formalize a relation among images and pixels in images to a perception contract, we can't really use any sort of verification approach here, right? I wouldn't know how to do that yet. So I think the only course that we have for now is to sample some states of the system and to gain as much confidence as we can of these perception contracts. So formally speaking, we propose perception contracts. So consider that we have a ML perception and a safety property fee for it. And now also consider that we have an ideal system with ideal perception, meaning that the estimate, GTE, that we know here, equals the ground truth. That's what we mean by perfect perception. And then assume that we have an inductive invariant that proves the safety property, phi, for the system working with ideal perception. A perception contract for a system is defined with respect to such an invariant. The perception contract relates ground truth and ground truth estimates, intuitively capturing the error ML-based perception is allowed to make. It is a symbolic formula in logic that relates ground truth and ground truth estimates and ensures the crucial property that if we start with the state satisfying the invariant and the environment on the state transitions to a new ground GT, and perception contract allows an error in ground truth estimate GTE, then the controller, reacting using this estimate as a result in a new state that continues to satisfy the invariant. And I point your attention to the predicate that is control of S on GTE produces this S prime, which is the next state. And that's sort of the key property here. And below you can see an example of what a perception contract looks like. We have these perception variables, y theta, and those would be the ground truth variables, and we have ye and theta e, which are the estimates. And as you can see, this formula is more or less bounding how much discrepancy can be between these values. So now we're ready to define the perception contract synthesis problem. Given an invariant of the system, given an invariant that the system maintains and shows the safety of the system and a set of pair of ground truth and their estimates, which we can assume also preserve the invariant, and a logic for expressing contracts. The goal of the synthesis problem is to find a perception contract such that the following two things hold. The given input set of pairs of ground truth and their estimates are included in the perception contract. And more importantly, the perception contract maintains the invariant for all the states S under the ground truth perception GT and estimates GTE from the given input images. Okay, so this is the problem. This is what we want to accomplish. Now, how are we going to build a learning algorithm to find these contracts for us? So to do this, we propose a learning approach called Perceptor. Each round, we begin with a set X of ground truth and estimate pairs, labeled positive or negative based on if they preserve the invariant. The learner synthesizes a classifier that separates the samples in X and proposes it to the teacher, which then checks whether the pairs of ground truth and ground truth estimates defined by the contract maintain the invariant. And that's sort of like the key point that I want to make in this slide is that the teacher, in this case our constraint solver, will check for each candidate perception contract whether that following constraint holds. If it does not, the teacher will give us back a counterexample, which is a GT-GTE pair that it's included in the candidate perception contract, but not in the invariant. Now, in terms of implementation details, for the learner, we use a decision tree learner that we modified to be an exact learner. So it's a consistent classifier, doesn't make mistakes. as for logic, we use quantifier-free formulae and Boolean combinations of octagonal constraints and real value functions with upper and lower bounds. For our teacher, as I mentioned, we use Gurobi, which is a constraint solver based on mathematical optimizations. And this sort of takes us to, okay, so now we've proposed perception contracts. It's there, but it's not there. Okay. So now we've defined perception contracts. I've told you defined our synthesis problem. I've defined a way to synthesize these. So now, I guess, we have to put it to action, right? So to evaluate our approach and the utility of perception contracts, we use two case studies. One is a lane tracking system on a Polaris Gen E2 electric vehicle, and a crop follow system, an agricultural robot that follows crop. Although these two systems might be similar at first, they are significantly different. For example, the neural perception for the lane tracking system is LaneNet, which is a very large model. It's 18 layers and over 3 million neurons. The controller is the Stanley controller. And we collect over 24,000 GT-GTE pairs for synthesizing a perception contract. The crop follow is just a different neural network, is ResNet 18. And for that one, we collect over 7,000 GT and GTE pairs. Something I do want to point out is that these systems are proven to be formally safe under perfect perception. And as you will later see, with neural network perception, these systems are not safe. So we make some design decisions to address this. So continuing on this, as part of our evaluation, we set up an environmental model, as discussed earlier, and we define sort of the perceptions that these systems are estimating. The perceptions in this case is D, which is the relative distance, and psi, which is the heading angle. And these two precisely describe the location of the vehicle. The invariant for these two case studies has a similar shape, but different sort of V functions here. And the invariant is saying that they require that the system, when the system is evolving, the error they make is always not increasing. This V function takes a ground truth estimate values of D and psi, and now puts a non-negative real value representing the distance to a desired state. So for example, in the lane tracking system, a desired state would be when D is 0 and psi is 0, because that means that the vehicle is perfectly aligned with the center lane. So in our case, the B function for this case study is simply a distance function from that particular state to the origin. The other thing I wanted to mention is that, as I mentioned, these systems are not proven to be safe with neural perception, correct? So we take the space of all the state space of ground truth perceptions, right? So all the possible locations where the vehicle can be, and then we partition them based on if they're safe or not safe. So as you can see here, this vehicle is facing away from the center lane. So that in that sense, it will be unsafe. Okay. Sorry about that. Okay. So here I we discussed our approach, the results of our approach. So as you can see here, we have various configurations for a feature space. This feature space defines sort of the kind of constraints that, that the decision tree learner has access to. But the main takeaway here is that you can see that on regions that are safe, meaning that there are no GT-GTE pairs that violate the invariant, and the region is unsafe when there exists at least one GT-GTE pair that violates the invariant. So on safe regions, you can see that our approach is very good at finding perception contracts. So I think the main takeaway is also that we can learn these perception contracts effectively, and we can do so in a reasonable amount of time. Excuse me. Now, I want to sort of illustrate these pictures in context, so it makes a little bit more sense. As on the left, you can see is the region of ground truth values. So blue indicates that that region is perfectly safe, and then the black arrow indicates sort of how the vehicle would be positioned. On the y-axis, you will find the relative heading angles in degrees, and then the relative distance on the x-axis. So as you can see, that when the vehicle is positioned sort of further away from the center of the lane, the system is unsafe, and so that sort of makes sense, right? Violate the invariant. And also on the top right. And as you can see for one of the results where we cover all the cases, we have a check mark, and that's sort of how you can see how we find perception contracts. So the last thing I want to discuss is runtime monitoring. I think we can use runtime monitoring. We can use perception contracts for doing runtime monitoring, and this is something that we wanted to sort of evaluate. Right? To do this, we validate perception contracts within the context of closed-loop systems. And then, so we run these systems with simulation. We collect the traces, as you can see there in the results in the table, and then we compute sort of the precision. So now, as you can see here, the main takeaway here that you can see is that our results indicate that PCs can be effective during runtime monitoring and can alert users of problematic regions in safe problematic regions. So because in safe regions, it agrees with the invariant very well, but we notice this pattern that in unsafe regions, although the precision doesn't drop significantly, it kind of is indicative that, okay, so it's not agreeing with the invariant so much, so maybe there should be some sort of debugging that needs to happen. So just to culminate, another reason why we can use the invariant for runtime monitoring is because, in this case, the invariant says that this perception, which says that we have two-lane road, it's okay. There's no error here. But our perception contract, because it checks against all states for a given perception, says that at faster speeds, but reasonable, at fastest but reasonable speeds, the perception causes the system to break the invariant. That is all that I have, and now I'm ready to take some questions.
We have time for like one quick question if anyone has one. Why don't you go set up? Let me ask a quick question. So any thoughts on like sensor fusion? So you're in these systems, you're often dealing with like multiple sensors that are sort of, you know, monitoring the road or something. Any thoughts on how this might fit into that? Any thoughts on sensor fusion, where you have, say, multiple sensors, say LiDAR plus, you know, a normal vision camera, for example, sensing the same thing, and when they disagree, like how would perception contracts fit into that kind of system?
So the notion of
Please, microphone.
Oh. So in a setting where there's multiple sensors, are you saying that would that be a problem for perception contracts?
Yeah, just your thoughts on that.
No. So no, I don't think so. So because generally speaking, yeah. So we want some inputs, could be images, and whether it's come from sensors. We're working at the level where we just care about the output of your perception module, whatever that is, right? And yes. Can we take this one offline?
Sure.
Thank you.